All right, now we're moving into another problem that's in 40. And this one is fun. Oh yeah, it's a lot of fun. Now, let me explain what's happening here. We're doing the same thing that we did with the last problem, right? The last problem we did, the first thing we did was do the RD. Okay, we're given the formula here, so we're going to figure things out by RD. And surprise, surprise, because it's the same formula as the last problem, we've got a RD value of 4, which is a giveaway for an aromatic ring. Remember, you see 4 there. The first thing you want to do is say, I've got to confirm if it's an aromatic ring. And look right up here, right around 7.21, you've got a complex pattern there. And it integrates to 5, and that's a dead giveaway for a monosubstituted aromatic ring. So the good news is that we don't even have to really look at this too hard. We already know, just by looking at it, that it's going to be a monosubstituted aromatic ring. The weirdness for this problem actually comes on what's attached to the aromatic ring. Okay? So we're going to come down here to 4, 4.0, and we have a hextet. And that hextet, and we can tell it's a hextet because if you look at it, you can actually see it here. I've got 6 different peaks. 1, 2, 3, 4, 5, 6. That hextet is a giveaway that I've got 5 hydrogens on either side. Okay? It integrates to 1, so I know it's a CH with 5 hydrogens around it. It's a hextet. And what that's going to tell me is that I've got a CH with the CH2, a CH3 next to it, and because it shows up at 4, I've got an oxygen attached to it as well. Right? If you look at this and you count the number of carbons, this pretty much tells us what the rest of the structure is. But I do want to explain something else that comes up here, and that's what happens at 2.8. Now, if you look at 2.8, and I'm going to zoom in here on this particular part. Right? If you zoom in on 2.8, you'll see, or 2. I put it at 2.8, but it's really right around here, 2.72. It doesn't really matter. You can see that this is a complex splitting pattern. All right? It's complex, but from what I put together on this particular table, I know that it's got to be something of this form. Okay? So where is the aromatic ring going to be attached? There's only one place it can be attached, and that's here. Okay? We know that it doesn't have any hydrogens, so why is the splitting pattern for this particular structure so strange? Okay? And that has to do with the fact that this CH2 and this CH, again, this is chiral and this is something called prochiral. Both of these things are going to exhibit some weirdness as far as coupling goes because they've got chiral states or possible chiral states due to this hydrogen here. Okay? As a result, what ends up happening is that you get something that's a non-first order coupling, and that's what we see up here with this weird structure. All right? So again, we're looking at something, this CH2 is prochiral, this CH is chiral. So as a result, there's 2 different forms here, and it really messes up the coupling that goes on here. It becomes a non-first order type of coupling, and it's not something you can really predict. So again, that makes this thing a multiplet. Okay, I can solve what this is. You guys can't solve it. I'm not going to expect you to be able to solve what that is. So if you see something like that, just label it a multiplet and move on. There's no reason to banging your head against the wall trying to solve something like that. It's got 2 hydrogens, so I know it's a CH2. So I know that this thing has something around the side of it. Okay, because it's such a weird complex multiplet, I can't really tell what that thing is. Okay, so let me zoom out again. Now, if I look at this thing, I've got a singlet. It's got 1 hydrogen. Okay, and then I know from its shape and its little broad thing up here that that's going to be an OH peak. Okay, and then down here 1.21, 3 hydrogens. 3 hydrogens generally means a CH3, and it's a doublet. How do I know it's a doublet? It doesn't look like it here on the spectrum, but it's provided right here. 1.21, I do see a doublet. Okay, so I know it's a doublet. and I know from that point it's a CH attached to a CH3, which just confirms that this hypothesis is correct. Right? So my solve for this problem is the aromatic ring is attached to the CH2, attached to the CH, attached to OH, attached to CH3. I didn't even have to do these three things because I knew from just this one peak, it gave me enough information that I was able to deduce that there's a CH2 here, a CH3, it's attached to an O, and that's an H. Okay, because I know my molecular formula, this pretty much fell into place, and I was able to deduce everything from that one little peak. See, isn't NMR grand?